Hi, today we're going to chat about symmetric functions in college algebra. We can test for symmetry a few different ways. Our function can be symmetric about the x-axis, the y-axis, or the origin. If it is symmetric about the x-axis, we will replace y with its opposite value, and if we obtain the original equation, then we know our graph is symmetric with respect to the x-axis. If we replace x with the opposite of x and it produces the equivalent equation, we are symmetric about the y-axis. This is also known as an even function, and we'll talk about this in a little while. If it is symmetric about the origin, we need to replace both the x and the y value with their opposites, and if it produces an equivalent equation, then the graph is symmetric with respect to the origin. This is known as an odd function, and we'll talk about that in a little bit as well. Let's start with our first picture of the equation x equals y squared. If I want to determine that it is, in fact, symmetric about the x-axis, notice that I'm replacing my y value with the opposite of y, and I know that negative y times negative y is y squared. So I see that if I were to simplify, I would end up back where we started. So it is symmetric about the x-axis. Looking at our middle equation, I want to determine that it is in fact symmetric about the y-axis. So this time I'm going to replace my x value with its opposite. When I do that, I know that negative x times negative x is in fact x squared. So I do end up back where we started. So it is in fact symmetric about the y-axis. So we see that it does mirror across our y-axis. If it is symmetric about the origin, we will replace both our x and our y value with its opposites. And when I do that, I know negative x times negative x is x squared, and negative y times negative y is y squared. So I do in fact end up back where we started. So it is symmetric about the origin, and we can see that our points do reflect straight across the origin. Let's test to see if y equals x squared plus 2 is symmetric with respect to the x, the y, and the origin. So we'll start with the x-axis. If I want to determine if it's symmetric about the x-axis, notice I'm replacing y with opposite of y. And when I do that, I'll have to divide everything by -1 in order to get y by itself. So when I divide everything by -1, I end up with y is equal to negative x squared minus 2. I see that that does not match my original equation. And since it does not match the original equation, I know that it is not symmetric with respect to the x-axis. But perhaps it's symmetric against the y-axis. So if I want to find symmetry against the y-axis, I will replace x with negative x and simplify. So negative x times negative x is positive x squared. And since I see that it is the same as our original equation, I know that it is in fact symmetric with respect to the y-axis. Let's determine if it is symmetric about the origin. So when I determine if it's symmetric about the origin, I have to replace both x and y with its opposite value. So I'm going to change y to negative y and x to negative x. When I simplify, I see that I end up with negative y equal to now positive x squared, since negative x and negative x is positive x squared. Divide everything by -1, and when I divide by -1, I see I get y is equal to negative x squared minus 2. And unfortunately, that does not match our original equation, so it is not symmetric with respect to the origin. Here's our graph of y is equal to x squared plus 2, and I can easily see that it is symmetric about the y-axis as it mirrors itself across the y-axis. It does not mirror itself across the origin, nor does it mirror itself against the x-axis. Let's try x squared plus y to the fourth equal to 5 and test for symmetry. Here's what the graph looks like. So as we go about, we can see and verify that what we see in Desmos matches what we see and find out algebraically. So when I look at the x-axis to see if it's symmetric, I visually can see that it is, so our answer should be yes. But I replace my y value with the opposite of y, so negative y. Notice that I have negative y to the fourth power, so if I'm multiplying negative y by itself 4 times, it's an even amount, so we'll still end up with positive y to the fourth. We obtain the original equation, so we see that it is symmetric with respect to the x-axis to verify that what we see visually matches algebraically. I also see visually that we are symmetric about the y-axis. We mirror ourselves across the y-axis. To algebraically determine this, I will replace my x value with negative x. And when I do that, take negative x times negative x, I end up with x squared plus y to the fourth equal to 5. This time I also see that it matches my original equation once I simplified, so it is in fact algebraically symmetric with respect to the y-axis. Is it symmetric about the origin? I can visually see on our graph that it is, so let's verify algebraically. I need to replace both my x and my y with their opposites. When I take negative x squared and simplify, I end up with positive x squared plus positive y to the fourth equal to 5. And again, this matches my original equation. So it is in fact symmetric about the origin. And this time it was symmetric about all 3. It's not always going to be the case. As we saw in the previous example, it could just be one of them. Let's talk about even and odd functions. An even function is also symmetric about the y-axis, and an odd function is symmetric about the origin. Our goal here first is to determine what happens if I plug in the opposite value of x. One of 3 things will happen. I will get my original function back, in which case I know that it's an even function. I will get the opposite signs of all my function where I originally started from, so it will be odd, or neither will happen, so it's neither even nor odd. I have the function 5x to the 7th minus 6x cubed minus 2. I can see right off the bat that it is not symmetric about the y-axis, so it's probably not going to be even. I also see that it is not symmetric about the x-axis. However, I do see that my points go across the origin, so it's most likely going to be an odd function as it is symmetric about the origin. Let's determine this algebraically. So I have my function 5x to the 7th minus 6x cubed minus 2. So I'm going to replace all my x values with negative x to see what happens. When I plug in the x values, I see that I end up with negative x to the 7th power, so that's an odd amount, so I'm still going to have negative x. When I multiply negative x cubed, I end up with a negative x times negative 6, which is positive 6, and negative 2 times negative x is positive 2x. I do see that f of negative x, when I plug it in, does not equal the regular function itself, so I know that it is not even. So for sure our function is not even. Let's determine though, because I do see when I ended up with my signs here, all our signs were opposite from the original. So if I look at my given signs that I found after I plugged in my negative x, and I compare them to the signs up above, notice that they're all opposite. I went from positive to negative, negative to positive, and negative to positive. So my signs were opposite of what I had. Therefore, I know for a fact that my function is odd. Let's try one more to determine if it's even, odd, or neither. I've graphed this function. I can see that it reflects across the y-axis, so I can assume that it would be even. It does not reflect across the origin in any shape or form, so I know that it's probably not going to be odd. Let's see what happens when we plug in negative x into our function 5x to the 6th minus 3x squared minus 7. So I'm going to plug in negative x to see what we end up with. Negative x to the 6th power. Notice here that I have negative x multiplied by itself 6 times, giving me a positive value of x, so 5x to the 6th. Negative x times negative x is positive x multiplied by negative 3 would give me negative 3x squared, and then minus 7. I see that that matches identically to where we started. And since that happens, we ended up back where we began with the function itself. I know that the function is in fact an even function. A function can be either even, odd, or neither. It can't be more than 1. So therefore we can stop and we don't have to continue testing once we determine if it's even, odd, or neither. We can stop. We don't need to continue on further. And now you can successfully work on your symmetry homework for college algebra. Thanks for joining me today.